Okay, so this is the second half of lesson 3.3. So I'm calling it 3.3b. And in this one, let's start with kind of work in reverse. So here's a graph. There's the feasible region, that kind of solution region there. And I want you to figure out what the inequalities would have to be. And this one is not too bad because they're all horizontal or vertical lines. So let's think about what restriction would cause a horizontal line right there. So that would be, let's see, that would be a horizontal line, so it's y. And the value looks to be about 3, so 3. And the shading looks to be below the horizontal line, so I would say less than or equal to because it's a solid line. So that restriction would shade below that line. In a similar manner, this one is also horizontal. It has a y value of -3, and that one looks to shade above, so greater than or equal to. So uh, that would give you kind of the area in between those two. If we look at this vertical line, that's going to be an x equals line. So x is vertical, -3. Looks like we're shading to the right, so that's bigger than or equal to x. It's a solid line again, so I would definitely use the equal to symbol there with inequality. And here, x is vertical, 5, and that's going to be smaller than or equal to 5. And if you have all those inequalities together, it forms this feasible region, right? That shaded region there. Okay, a little bit tougher. So go ahead and stop it. See if you can try this one on your own. But I'll go ahead and do this since I don't have to stop and wait for you. So like it really helps to kind of identify a couple points. So you can see those 2 points right there. So like the y-intercept. So if you think about y equals mx plus 5, so y equals, or I guess I shouldn't say equals. We're really gonna figure out if it's equal or less than or whatever. So that the y-intercept is going to be 5, and the slope looks to be, let's see, if you count up 2 units and over 3 units, both in the positive direction, so the slope is 2/3. And the inequality sign will be smaller than or equal, so we're shading down, so less than or equal to. Again, none of these look to be dotted lines, so I think we've got that. Let's try this one. So the y-intercept again is 5, so we're going to have plus 5 there. The slope looks to be, if it goes up 2, that's positive. It goes left 3, so -3. So it looks to be rise over run, so -2/3. So almost like the other one, but it's negative. And less than or equal to, we're shading below that one, so less than or equal to. And this one right here, identifying those 2 points there. So the y-intercept is 1, so +1. Slope looks to be up 2/3 in the negative direction. So just like that other line, it looks parallel to it. It's actually a -2/3. And y is above, we're shading above, so greater than or equal to that one. And this line, right, nice y-intercept there at 3, so +3. I'm sorry, +1. So y-intercept is 1, sorry. And then slope looks to be up 2/3 to the right, so 2/3. So 2/3, just like the other line that's parallel to. And y, and we're shading above that one, so greater than or equal to. Okay, this is a little bit more of a challenge, so go ahead and stop it and try to identify the restrictions here. So you have to identify a couple points here. So that line looks something like this. And so the y-intercept looks to be 0, so +0. Slope looks to go up 3/1 in the positive direction, so 3x or 3/1x. And the inequality, we're shading below that, so less than or equal to. Again, it's a solid line. So this one actually is a little easier there because it's just straight horizontal. So y at 3, and the slope is 0 essentially. And so we're shading below, so less than or equal to. And this one, again, not too bad. Again, it's a y line, the y is 0. Shading above, so greater than or equal to. And the toughest one, I think, is this one. So you can see here it's got a slope of positive 3. I'm going to make a few more slope points. So I'm going down, and I'm kind of running out of room here, but if you did keep going, it would go down 3 more to negative 9, and that'd be at 1 for the x-axis. Go down 3 more to negative 12, and that's going to be on the axis. So I think there's a point down there at 0, comma, negative 12. It looks to me. So just kind of keeping the pattern in line. You could have figured it out algebraically by plugging in, like pick a point here, like 4, comma 0. Slope is 3. And like plug those in for x and y, plug into y equals mx plus b. We could algebraically figure this out. I just thought it was easier to find out the graph. But you can find that b equals negative 12 either way. Okay, so our b is negative 12, so minus 12. Our slope is positive 3 for this line, so up 3 over 1. And we're shading above the line, so greater than or equal to. So those 4 restrictions will make that feasible solution region right there. Okay, so now we'll get to good stuff here. So let's try this. So this is kind of a word problem. This is where we're headed with this. I want to get you ready kind of for the next lesson here. So suppose you purchase a 750 square foot piece of property and you're going to make a parking lot, make a lot of money. Each car takes up 5 square meters. Each bus is a lot bigger, takes up 30 square meters. But due to city regulations, you can't have more than 70 vehicles parked in a lot at a time. Okay, so you want to maximize your profit. We'll get to the actual profit here in a minute. Let's try to draw this graph and come up with a couple of equations. I like this number right here because I'm thinking, okay, there's buses and cars. So you could say something like, cars plus buses equals 700. And let's just solve that for C. We could solve for really either one, but I'm going to subtract B, so I get negative B plus 700, or 700 minus B. Okay, so that's our first equation. Our second equation has to do with the number of square meters each one takes. So we've got 5 times C, I think, right? Plus 30 times B equals a total of 750. So what you want to do is solve that one for C. So we get 5C equals negative 30B plus 750. Divide by 5, C equals negative 6B. I think that's 70 when you divide by, does that make sense? Let's see. No. Maybe 150? 150 times 5. Okay, so plus 150. So I'm just going to count up. I'm going to say this is 0, 0 right here. 1, 2, 3. So that's going to be 30. I guess we'll say this is cars, or C over here. 60, 90, 120, 150. And we're going to make this one buses, and we'll go 30. I'm just trying to economize a little here. You could label every 10 if you want to. 120 and 150. That should be enough. We'll see. Okay, so according to this, the line is there's 2 lines here. So let's do I guess the blue line first here. So if we're going to graph this one, let's just do the y-intercept. I'm going to do this one in blue, so it's 700 for cars. Oh, I didn't make this. No, this is not 700. This is 70. Sorry. I think I wrote down the problem wrong. So 70 is the number of vehicles. So I was like, wait, there's not 700 cars. That's what it is. Okay, so that makes a little more sense. I guess I was confusing the two. Okay, so we have C plus B equals 70. That makes a lot more sense. There's 70 vehicles total. So the y-intercept there is 70. So right about there is the y-intercept. The slope is the opposite of B. So the slope is -1 essentially there. So the number in front of B is -1. So slope of -1, these are going by tens, but I think -1 will work about the same because they're labeled the same both ways. So I'm going to make a bunch of slope points here. And I'm going to draw a solid line because I think these are all. So there's the blue line there, the blue graph. And let's check this one. So this one, we solved it for C. So the y-intercept is 150. Okay, that's right up here. And the slope is -6. So I'm going to go down 6 over 1, down 6 over 1, down, well, I mean, kind of run out of room there, but something like this. Okay, so we have this kind of feasible region. So this feasible region is um, kind of implied in this, but I guess we could write them out. Uh, is that C, the number of cars, is greater than or equal to 0. The number of buses is greater than or equal to 0. In other words, everything in here is in the first quadrant. I kind of only drew it in the first quadrant, so it's probably understood. But I think it'd be good to go ahead and label we definitely need, this is one of our inequality, well, an equation. Um, I guess we could probably have these be inequalities, right? So we're saying the number of cars. Let's change this. So I didn't think about this. So really, we've got to think about the fact that this is really an inequality here. So the number of cars is no more than 70. So no more than, so it actually is less than or equal to. So we're shaded below that blue line, right? And really very similar for the so it's not really equal to 750, right? It can go up. You might not use all the area. You want to kind of maximize, so you want to use most of it, but it's not going to be any more than 750. So I think, unfortunately, we didn't divide by negative or anything. It's not going to change the sign. So I think that one also is a shade down kind of situation. So we've really got shading below the green line, below the blue line. And so that feasible region kind of has like this endpoint somewhere it crosses right in there. I can't tell exactly where. It crosses the axis right down there at 30. It crosses at 0, 0. So it has kind of like, I'm just going to kind of draw the feasible region. These are kind of the outskirts of the feasible region. I really need to find like that point of intersection. I want to find the ordered pair of that point. And I definitely don't know it. I know I can estimate it, but it's really hard to tell. So to really get it correct, you probably want to just go ahead and solve this system over here. So I'm going to try to solve this system. So I'm going to take this C plus B. I'm just going to use equals because I just want to find that point. So I'm not worried about inequality. And then the other one is 5C plus 30B equals 750. So I want to solve that system. We've done a little bit of that this chapter. So it looks like we could multiply maybe that top one I might multiply by -5 so that the C's would be the opposite. So I get -5C minus 5B equals -350. And then the second equation doesn't change. It'd be 5C plus 30B equals 750. We're going to add those two guys up. C's go away. We get 25B equals exactly 350. Okay, divide by 25. B equals, let's see, so 25 goes to 104 times. So that'd be 4 times 3, which is 12, and 2 more, so that'd be 14, I think. So B equals 14. So the B value is 14, and which means that you can plug it back in to this equation, right? So you'd have C plus B equals 70. So this would be C plus 14 equals 70. So you subtract 14 from 70, you get C equals, C at 70 minus 14 is 56. So we're going to say this is this point is like B comma C, right? So our B value was, if I look at it again, it was 14 for the intersection point, and our C value was 56. And so now the question is, we've got a nice graph here. The shaded area obviously is, inside of here, the feasible region. And we've got to try and solve this problem. Well, the problem asks us, it says you want to maximize, you charge $450 for cars, it's $975 for buses. How many of each type of vehicle would you need to park on the lot to maximize your income? I think we can safely say that parking 0 cars, that's not a good option, right? 0 cars and 0 buses, you're not going to make any money. But all these other 3 points, so this point here at 30, 0 for B and C, and this point here at, I think that was 70, 0, 70, 0, 70 for B and C. So those 3 points are points we have to test. In fact, when you have a feasible region like this, you only need to test the vertices of the polygon there. If it's a polygon, just test the vertices. You don't have to test every point inside of there. You can only test the vertices and you'll be just fine. So one of those points is going to be our answer. It'll maximize income. I'm guessing it's going to be this one if I had to guess. Although maybe parking all buses would be more profitable. I don't know. So the most you can have is 70 vehicles total. So some combination, just guessing that might be the highest answer, but we'll see. So what you need to get a calculator for this, but we're going to plug in to this formula, right? It says 450 for cars and 975 for buses. So the function to be maximized, I think there's a name for it. I'm just going to call it f of x, but usually we use a name. Is it p of x? There's usually a name we use, but it'll be fine to say this. 4.5, I guess that'd be C, plus 9.75 B. So we're going to find out which of those points maximizes the function. Okay, so if you plug in, let's see, this point right here, this leads to a profit of $682, 682.5. Okay, so let's plug in this point now. So I'm going to, whoops, go here, and we'll do 4.5 times 14 plus 9.75 times 56. 609, so this one leads to a profit of 609. Ooh, maybe that's not that. So I was thinking that might be the best point, but it's not looking so good. Let's check the all buses. If we go all buses, maybe that's the best. So this would be, maybe the cars are the best. I don't know. So 30, whoops. Let's go here. Okay, so 30 times 4.5, 4.5 times 30 plus 9.75 times 0. Wow. So I misestimated that. So this one would be 135. So the cars are a much better deal. If you own this lot, you want to park as many cars. You want to tell the buses, don't come near this lot. We want to pack it full of cars because that's going to give us the best profit. And so that's the kind of thing the business can actually use math to maximize their profit, to figure out what the best price points are for different items, etc. So we'll get more into that next lesson, but that will maximize our income to park all cars in our parking lot.